Yes, sir.
Okay, thank you. I would just want to go over a few things that we know already, but I just want to review it, 'cause especially you have to do it for the test that I sent out yesterday. I hope all of you got the test. It's due on Monday. Okay, we already said that the impulse response in the time domain is called h of n, and it's simply, the impulse response is simply the inverse z transform of the transfer function. That's the transfer function. On the other hand, the step response, the input step, okay? So x of z is a step, okay? A step, okay? The z transform of step times the transfer function. That's y of z. See it right here? That's y of z. And when you take the inverse z transform, you get y of n. You get this. And if x is step, then y of n is called s of n. We know all this. Okay. And then, of course, y of z is a product of h of z and x of z. But y of n is not the product. Y of n is the convolution. We did all that. Any questions about that? So let's do one last example then of the step response. And I'm going to switch slides. Okay. So we have a transfer function h of z. This is a question right out of the book. Okay. We want step response. S of n. What's the first step? What's the first step?
You get me?
No? You said something?
Oh, my Wi-Fi a little bad, but I was saying you can start by finding the impulse response.
Find what?
The impulse response, like you have the date.
Why are you going to find the impulse response when I'm asking you to find a step response? You don't need to find the impulse response to find the step response. Anybody else? Let's get back to what you said. How is finding an impulse response going to help you find a step response? Mr. Buchamp, can you hear me?
Yeah, I can hear you. No, that wouldn't help.
I'm wondering what you're thinking there. What are you going to do with the impulse response to get the step response?
No, that wouldn't help. You still have to multiply it by the.
What's the first step?
In the denominator, what if we multiplied? So that'll be 1 times 1 and then 1 times negative 0.9 c inverse. And then you'd have negative 0.1 c inverse times 1. Like,
expand the brackets? Is that what you're saying?
That's what I'm trying to say. So,
all right, why you want to do that?
I possibly change the look and we might see something similar in the table.
And to make it look similar to the table, what are you trying to achieve? We want to put H of Z in standard form. We want to put H of Z in standard form. That's the first thing we need to do. Put H of Z in standard form. All right, first of all, multiplying by Z. Top and bottom by Z. Okay. Okay. And then we multiply by Z again. Yeah, so now it's in standard form. Now what? You could have done what you want to do, Mr. Johnson. You'll get that eventually. So you want 1 minus 0.9 z to negative 1 minus 0.1 z to negative 1 plus 0.09 z to negative 2. Okay, so this becomes that's what you said. Now multiply top and bottom by z squared. 5z squared, z squared minus z plus 0.09. And then this factors into the bottom. Yeah, so now we have it in standard form. Now what?
Now we have to find the zeros, right?
Now you have to find what?
The zeros, no?
Why we have to find zeros?
It looks like we have to use partial fraction expansion.
No, we're not there yet. I'm not asking to find the inverse z of h. What am I asking to find the inverse z of? I want the step response. That hasn't hit home apparently. I want the step response. Previous page. What is step response? The input is a step function, which means the z transform is z over z minus 1. You have to multiply that by the transfer function. and then take the inverse z of that. So in describing all that a few minutes ago, you missed all that. So what we need to write is y of z, that's the output, is equal to h of z times x of z. Okay. Where x of z, where x of n is a step. So if x of n is a step, x of z is z over z minus 1. So y of z then, and that becomes s of z, because if the input's a step, then the output is automatically called a step response. Will be 5z squared, z minus 0.1, z minus 0.9, times z over z minus 1. This is what you have to find the inverse z of. This. Is that clear?
Yes, sir.
Okay. Let's do. So how are we going to do that? How are we going to do inverse z of 5z cubed over z squared minus z plus 0.09 times z minus 1? Because that's what so this is s of n. That's a step response. How are we going to do this?
And we have to use the division, the long division,
All right, why?
because it's a rational function, but it's not strictly proper yet.
Very good, young man. Very good. Because z squared times z is z cubed. So what we divide 5z cubed by? What do we divide 5z cubed by?
C squared minus C plus 0.09.
Really? That's what the top says? The top, this says, so what? You just throwing this away? Is that what you're going to do? Up here it says, divide that top by this bottom. That's what it says. So why are you only dividing by the quadratic part of it? You have to multiply the bottom. on this bottom, z cubed minus 2z squared minus z, no, minus plus 0.09. That's 1 minus plus 0.09 minus 0.91 z minus 0.09. Okay. Let's check that. Let's check that by checking the roots of this. Because the roots of this gotta be the roots of this. And the roots of this is from the previous page. The roots of the quadratic, 0.1 and 0.9, and then 1. So the roots of this should be 0.1, 0.9, and 1. So I'll check to make sure we did that multiplication right. So we define the polynomial. So actually, that's the denominator. This is called the denominator equals open bracket 1, negative 2, negative 0.91 minus 0.09, close bracket, and then we do roots of denominator. And I screwed up somewhere. Where did I screw up? So z cubed let's go through it again. Z cubed minus z cubed minus z cubed minus z 0.09 z.
I think it would be a positive z squared, not a negative. Wait, no. All right. No.
Did I enter it in right? 1, negative 2, negative 0.91.
That z is supposed to be positive, not negative.
The z,
Yes, sir.
so z cubed minus z squared. Yes. Yeah, I think you're right. Plus z. So that would make this plus 1.09. Change that then. $1.09. And now let's do the roots of that again. Yes, I got the roots I need. The roots are 1, 0.9, and 0.1. All right. So now that's what I'm dividing by. I'm dividing by all the denominator. Okay. So this is z cubed minus 2z squared
You're
plus
supposed to be
1.
showing your writing part?
Excuse me?
Are you supposed to be showing your writing part?
Yes, yes. Give me a second. Well, no.
Yeah, we can see it now.
Okay. Let me. Z cubed minus 2z squared plus 1.09z minus 0.09 5z cubed. Okay. So this goes 5 times. Okay. So 5z cubed minus 10z squared plus 1.09 times 5, 5.45z, 5 times 0.09 minus 0.45. And we subtract. So this is 0. So that becomes 10z squared minus 5.45z plus 0.45. So 5z cubed over z minus 0.9 z minus 0.1 z minus 1 is equal to 5 plus 10z squared minus 5.45z plus 0.45 over z minus 0.9, z minus 0.01, no, 0.1. Z minus 1. So now you see, this is rational. It's proper. And we can take the inverse z of it. I'm going to the next slide.
Oh, the guy right.
Yes.
Never mind. This octave thing blocking the bottom equation.
Oh,
Oh, the guy right. You can show the first page.
what, the very first page?
No, the second one now, not the last one before, the one before this one. All right, thanks. You got it.
Okay. So this is just algebra that I'm doing here. Okay. So we need to find the inverse c of this. So let's just concentrate on this part of it. What do I do with this?
Gonna be partial fraction.
Okay, give it to me.
It'll be a over open bracket z minus 0.9 close bracket.
No, I don't need brackets on it. Why do I
Okay.
need brackets on here? Go ahead.
Sorry. Is that plus b over c minus 0.1
Yes.
plus c over z minus 1.
Yes. And what's A going to be equal to? What's A going to be equal to?
That would be 10 z squared minus 5.45 z plus 0.45 over z minus 0.1 in brackets, open bracket, z minus 1, close bracket.
That's it?
And to be evaluated at positive 0.9.
Yes.
C equals 0.9. So this is 10 times 0.9 squared minus 5.45 times 0.9 plus 0.45 divided by 0.8 times negative 0.1. Isn't that right? And the top becomes what? 0.9 squared times 10 minus 5.45 times 0.9 plus 0.45. That's the top. Divided by the bottom. Negative 0.08. And so A is 3.645 divided by 0.08. Negative 45.56. That's A. What's B going to be? What's B going to be?
B is 10 c to the power of 2 minus 5.45 z plus 0.45 all over open bracket z minus 0.9 close bracket open bracket z minus 1. And sorry, z equals 0.1. It's positive 0.
Right? Did I make any errors there on the denominator?
No, sir.
So the bottom is 0.72. I hope you're all checking my work.
Looks good.
Okay. And And now C. Mr. Anderson, are you there? Mr. Anderson, are you there? All right. I guess he's not. What is C?
C would be 10 z squared minus 5.4 z plus 0.45 over open bracket z minus 0.9 close bracket times open bracket z minus 0.1 and evaluated at z equals 1.
So the top becomes 10 minus 5.45 plus 0.45, 5 divided by 0.1 times 0.9. 0.1 times 0.9. Reciprocal times 5, 55.55. Okay. So this becomes negative 45.56. B becomes 0.006944. C becomes 55.55. So now what do we do?
Z transform to the table.
Yeah? What do we do?
So we multiply the top and bottom by Z minus 1.
No. Multiply top and bottom by Z.
Z, okay.
So we'll have a Z here, and the bottom will give us Z to negative 1. We're multiplying by 1. Z to negative 1 times Z is 1. Z to 0, which is 1. All right. So we have a Z here, and out front here we have a Z to negative 1. We have a Z here, and out front we have a Z to the negative 1. Okay. And so the step response is it's a 5 plus that. It's a 5 plus this. And that was S of Z. So S of N be plus 5. Yeah, so S of N. What's the inverse Z of the first term?
Is it 45 point, no, that's negative 45.56, open bracket, 0.9 to the power of n minus 1, U of n minus 1.
Yes. And the second one?
Okay, the second one is that's plus 0.009 6944. Sorry, I was looking at the number. Open bracket 0.1, that's positive 0.1 to the power of n minus 1, U of n minus 1. And the last term should just be plus 55.55 U of n minus 1.
The last term? The 5?
Would 5 be plus 5 delta n?
Delta of n.
Delta of n.
Let's put that here. Delta of n. So that's our step response. That's our step response, which required a lot of work. It was tedious work, but it wasn't difficult. It's just tedious. Any questions about that? Well, the test that's due on Monday morning, you will have to find the impulse response and the step response. But I'm only going to grade one of them. Miss Anderson, are you there?
Oh, the guy already sent a message in the chat saying he coming back or something.
Yeah, but that's not good enough.
No, I just telling you because to let you know he in there.
Well, I want to know if he returned yet. You see, he's trying to tell me. Did I just see his mic turn on? Mr. Anderson, are you there? He's sending me a message. He'll be right back, but I don't know what the hell that means. To be Heyman, that could be mean you'll be back in a week. He'll be back on Monday. And yet he's pretending like he's in the meeting. If you have to leave the meeting, then leave the meeting, and then I could let you back into the meeting, and I'll know exactly how long you've been away. He's trying to be away without letting me know how long he's away. I don't know why students play these games. Because in the end, it's going to be, do you know the material or don't you know the material? All right. That's all I'm doing on impulse response and step response. Okay. What's the third kind of response we normally deal with? We'll deal with the impulse response, the step response, and what other response?
Ram?
Say again, please.
Ram?
No, we don't usually deal with ramp response. We could, but we don't usually deal with it.
The magnitude response.
Magnitude response of what? Magnitude response of a transfer function. But that's in Fricke's domain. That's not in time domain. What else? Go ahead. That again, that's in Fricke's domain. What other response we deal with in the time domain? sinusoidal response. The sinusoidal response, that's where we put a sinusoid on the input. And we find out what the output is, the sinusoidal response. We're not ready to deal with the sinusoidal response yet. And how do we get the sinusoidal response in 320? We use phases. We use phases to get the sinusoidal response. We converted the sinusoid to a phasor. We converted the circuit to the phasor domain. We got the output in phasor form, and we converted back to a sinusoid. We can do something very, very similar in a few lessons. And that would be the sinusoidal response of a digital filter. Okay. We did, I think somebody mentioned zeros today. We found the zeros and the poles. We did that a few lessons ago. Okay. And I sent you a octave program to do that. Let's look at that now. So let me get it.
Dr. Carter, the thing you sent us over the email, will we have to put that in our directory?
Not if you put it. Let me show you. Let me show you. Oh, I guess you don't know how octave works yet, eh?
I'm not expert yet.
No. You don't have to be an expert. This is just basic stuff. What you put in your directory is a file. This is not a file, is it? You could turn it into a file, but it's not a file. So, let me stop share. Share now my screen. And y'all see in my email, aren't you? Okay, you see my octave screen now, yes?
Yes, sir.
All right. So I simply copy that onto this line, paste it. There it is. Okay. And I hit return. And there's my full zero plot. And you notice this big circle. What do you notice about this circle? And what plane is this? What two-dimensional plane is this? This is not the S plane. It's the Z plane. The Z plane. In 320, it would have been the S plane. Now you see the which one of these are poles? How many poles? Go ahead.
I assume the poles is the circles.
No, the poles are not the circles. The circles are zeros. Isn't that obvious? Doesn't a zero look like a circle?
True.
I mean, students don't think at all. We got 2 poles, so we got 2 zeros. And for this transfer function. Okay. And we got 2 poles, those are the x's. Okay. And these poles are complex conjugates because the horizontal axis is the real part, the vertical axis is the imaginary part. What can you tell me? What can you tell me about the circle? Tell me something about the circle.
It's like one wide. No,
It's
no, two wide and too high.
Yeah, man, please read the scale, okay? And don't tell me this was too wide and too high. Please read the scale. You don't see the scale on the x-axis and on the y-axis?
I see the scale. It starts from -1 and go to 1.
What's the origin of the circle? What's the center point of the circle?
0.
No, the point is not 0. 0, 0 is a point. This is a two-dimensional plane, two-dimensional graph.
Okay.
A point
0.
is not one number. A point is 2 numbers.
Okay.
Point, the center of the circle is right here at 0, 0. See here? Okay. The x-axis is 0. The y-axis is 0 at that point right there.
Okay, 0, 0.
So we know the center of the circle is the origin of this graph. What else can you tell me about this circle?
I mean, yeah. I enjoy it though.
Who's talking and not talking to me? Mr. Johnson, are you talking to me? If you're not talking to me, please turn your mic off.
All right.
Let me try Mr. Anderson again. Are you back, Mr. Anderson? I have a good mind just to kick him out of the meeting, and then he won't be able to rejoin. Folks, you can't tell me anything else about the circle? What's the radius of the circle?
The diameter is 2.
I just asked you about the radius.
Oh, the radius is 1.
Radius 1. The radius is 1, therefore it's called a unit circle. A unit circle because the radius is 1.
Got it, got right.
Yes, go ahead.
When you say unit circle, that's the same one like within calc, right?
Yes.
Right.
All that means is the circle has a radius of 1. And not only has the circle has a radius of 1, but the center of that circle is at the origin. Except here, the x-axis is the real part of z, and the y-axis is the imaginary part of z. So, what's the value of one pole? Sorry, 1, 0. What's the value of 1, 0? Give me the value of 1, 0.
Can I make a guess?
No, you can read the graph.
I was looking at the graph.
Well, why do you have to guess if you're reading the graph?
I assume the first zero would be at -1.
-1?
That's a,
I don't know what you mean by the first 0. Do you mean a 0 on the left?
yes, sir.
Yes, that's correct. And a 0 on the right? What's that?
+1.
+1. So we know we know the zeros. We know the zeros. We just read them. Give me a pole. Give me the value of a pole.
It would look like 0.6, 0.7.
You must be
No.
cockeyed. Are you cockeyed? Folks, look down here. You see where my cursor is? To the left, to the bottom of the screen? You see that?
My Zoom thing, it don't show that piece. I don't know what that is. So
Okay. How about this? You see it now?
yes, sir.
Now I go here to the pole. What's it read? What's it read?
That guy, you see how this is two-dimensional? You have 2 points. Do I give you the 2 points, or is it?
You have to give me the 2 points because that point has a real part and has an imaginary part.
Yes, sir. So
What's the real part?
The real part would have to be the x-axis. So that would be the. I'm assuming
The negative
that'd be the
0.3.
Negative 0.37608. You can read that value right there. That's why I made it smaller. Again, everybody see the left hand side, the bottom left hand side of the figure 1. When I move my cursor to the pole, it reads that value for me. It reads the value of that point. So that point is roughly negative 0.3555 minus j times 0.4168. And then you go up to the next one. It's its complex conjugate. It's the same thing, except that instead of being minus j, the top one is positive j. All right, now let's let's do this from scratch. You said to me, oh, film's getting in the way. Let me move it away. Okay. Let me close that out. So I'm going to create a file now, Mr. Johnson. I'm going to create a file. And I'm going to edit. Let's call it poll 0. Poll 0.m. Okay, yes, I want to create it. And now I'm going to create it. I'm going to paste exactly what I pasted earlier. And what happened? Oh, I pasted in the wrong way, the wrong place. And is there undo button?
Yeah, the yellow one up top.
All right. And let's go back down here. Let's paste there. Okay. So now I save this. Now I go back to the command window and just say, call up the file. Okay. And then I get exactly what I had before. Okay. Now let's actually do one. Let's do one from the book. You all see in my writing pad now, yes?
Yes, sir.
Okay. So here's the transfer function. Okay. What are the poles? How many zeros are there? Let's do zeros first. How many zeros are there?
And 1 0
Yeah, where's it located?
in the numerator.
What is the value? Is that it's 0?
.2.
Yes. Z minus 0.2 equals 0. Therefore, Z pole is 0.2. Z0, I should say. Z0 is 0.2. Where are the poles?
Do we have 2 poles?
No, we have three. We have 3 poles. You don't see Z cubed?
Yes.
We have 3 poles. Z squared times Z minus 0.7 equals 0. So Z squared equals 0, which means Z equals 0 and Z equals 0. And then we have Z minus 0.7 equals 0, which means Z equals 0.7. Right. So this is pole 1, and this is pole 2, and this is pole 3. All right. And now let's put this, what happened? Let's put this in octave. Okay. So I go to editor. Y'all see my file?
Yes, I see
Oh,
it.
okay. So what's the numerator going to be? The numerator is going to be what? The numerator is 1, 1, negative 0.2, isn't it? And what's the denominator? What's the denominator? This here, the numerator, that's just that coefficient 1, and then that coefficient negative 0.2. Now the denominator, what's the denominator? Well, we need to expand this, z cubed minus 0.7 z squared. Okay. So this here is 1, 0. No, 1 minus 0.7, 0, 0. Okay. Z cubed.
Question, Dr. Godric.
Yeah, go ahead. Z
When we put it-
squared.
When we put in octave, you put the 2 zeros to the back of it, just like that.
Well, if you just put 1 negative 0.7, what it's going to think this is z, and that's negative 0.7. If you just put 1 negative 0.7, octave's going to say this is z minus 0.7, isn't it?
Yes.
All right. So let's try that. And let's see if we get the answer we need. So we go back here, and the denominator is 1, negative 0.7, and 0, 0. Okay. And then we take the z-plane, and we save this. Save file. And we go back here, and call it up again. And there it is. Okay. There's our pole at 0.7. There's our 2 poles. Okay. See one on top of the other? And then there's our 0. There's our 0 at 0.2. Now, cast your mind back to 320. Although I do admit this diagram is a bit misleading because it looks like there's a 0 at 0, but that's not true. There are two poles there. They should really put a 2 there instead of circling it. Okay. Cast your mind back now to 320. When was the system stable? When was the transfer function stable?
Loss on all the poles was on the left hand side.
Yes.
Yes.
Now, what do you think the rule is for a transfer function in a z-plane? What do you think the rule is?
It'd be the opposite, like on the right hand side.
No. No. Why do you think they made a big deal about this unit circle? Why do you think they give us a unit circle? We didn't need a unit circle in the S-plane. The unit circle, where the pole is located with respect to the unit circle, determines stability. So this pole right here, is inside the unit circle. Therefore, this is a stable system. If this pole was on the unit circle, if it's on the unit circle, then we have marginal stability. If the pole is outside the unit circle, then we have an unstable system. So what do we say about the math then? What is needed for the pole to be inside the unit circle? What's the math criterion for that? What I'm asking is, without drawing the pole zero diagram, how do you tell if it's a stable system? If the system is stable?
Does it have to be less than, not greater than 1?
Excuse me?
Should the poles be like greater than -1 and less than 1?
No. Then how do you count? How do you count for what we had in the first graph, the pole zero diagram? How do you count for a complex number? Then let's go to what we had before. If I remember what that is. I don't even remember what that is. Is it up here somewhere? Oh, right here. The numerator is 1, 0, -1. And the denominator was 1.7.3. So let's do that again. So numerator 1, 0, -1. And the denominator 1.7. Point 3. Do that again. Okay, there we go. See the poles there? They're inside the unit circle. And they have an X value and a Y value. So you can't say between -1 and +1, the X value. That doesn't determine whether or not the pole is inside the unit circle. It's not the value of the pole that matters. It's the value of the magnitude of the pole. The magnitude of the pole the magnitude of this pole here, the magnitude of this pole here is you square the x value, you square the y value, take the square root of it. That's the magnitude. And that magnitude would be less than 1. All numbers inside the unit circle has magnitudes less than 1. All numbers on the unit circle has magnitude 1. And all numbers outside the unit circle has magnitude greater than 1. So it's the magnitude of the pole that matters. If there's a pole with magnitude greater than 1, the system's unstable. If your poles are on the unit circle, then you have marginal stability. And being on a unit circle means the magnitude of the pole is 1. And if the magnitude of the pole is less than 1, that's where you want to be. You want a stable system. Any questions about that? Let's look at
To calculate one question.
Go ahead.
What happens when one of the poles is outside of the circle and the other one is inside?
Well, from 320, what happened then? What happens when one of the poles was on the right hand side and all the others are on the left hand side? What happened then?
Is it marginally stable?
No, absolutely not. No. If there is just one pole on the right hand side, the system is unstable.
Oh yeah, unstable.
So if there's just one pole outside the unit circle, the system's unstable. What was modular stability in 320? Where were the poles located? Where are all the poles located for marginal stability?
On the margin, 0.
What do you mean on the margin? On the y-axis.
Yeah, on the y-axis.
On the y-axis. All right. Let's do another one.
The answer to the Tory question was unstable, right?
Yes. Well, I don't understand why is there any doubt?
No, I had to drop off the meeting for a minute. I just
Okay. All right. Let's do this one. Is this transfer function stable, unstable, or marginally stable? What's the first step? What's the first step?
That Cartwright, do you still have to like turn it to strictly proper, or you don't have to do it no more?
You have to put it in standard form. I don't know why we have any doubt about this.
Yeah, you just multiply the top and bottom by c squared.
Yeah.
So why was there such a delay in answering?
I'm trying to give someone else a chance to answer, man. I can't answer everything.
Yeah, okay. The rest of you should feel pissed off because of that comment he made, but it's probably true. Okay, there you go. Where are the zeros? Where are the zeros?
The numerator.
What are their values?
Is it plus minus 0.5?
No. When do you first learn? When do you first learn factorization? Is that like grade 10? How is it we can't do factorization? You want to know when that is equal to 0. To know when that is equal to 0, you have to factorize.
That's 0 and
0 and 0 minus 0.5.
But yeah. Equals 0.
So z equals 0 or z equals 0.5. That's where your zeros are. Where are your poles?
you make the denominator equal to 0.
Z squared minus 0.4z plus 0.5 equals 0. So what are your answers? So where are the poles located? So how do you find out? I don't think you old folks are studying.
So the Cartwright, you have to put in the quadratic formula.
All right, give it to me.
That's 0.5 plus or minus square root, open bracket, negative 0.
Oh man, it is z equals 0.4. I don't know where you get 0.5 yet from yet. B is net. Excuse me?
I didn't say 0.4.
No, you did not. You said 0.5.
I was meaning 0.5 mistake.
0.4 plus or minus the square root of 0.4 squared. Well, you can put negative there if you want. Minus 4 times 0.5 all over 2. Okay. So that's 0.4 plus or minus the square root of negative. Negative. Okay. It's 4 times 0.5, that's 2. Okay. Plus 0.4 squared. Try that again. 0.4 squared minus 2 minus 1.84 over 2. So that's 0.4 plus or minus j 1.84 square root 1.356 divided by 2. So the two poles are at 0.2 plus or minus j divided by 2, 0.6782. So is this system stable? Is this transfer function stable? How do I tell, folks? I just gave you the info a couple of minutes ago. What do I want to know about the poles? What do I want to know about poles? Excuse me?
Magnitude has to be less than 1.
All right. So what's the magnitude of these poles? The magnitude is the square root of 0.2 squared plus 0.6782 squared. And the magnitude is the same for both of them because they're complex conjugates. 0.2 squared plus 0.6782 squared square root is 0.500. So the magnitude of z is less than 1, stable. Any questions about that? Let's see that. Let's see that in action. Let's
I
see
think
that.
that's 0.5.
Excuse me? Let me try again then. No, of course not. The answer can't be 0.5. You know why? Because it's less than 0.67.
I get
So 0.6782 squared plus 0.2 squared. Oh, I didn't take the square root. That's what happened. Square root 0.7
Is 0.71.
0.71 less than 1. So stable. Let's do this. Add it to. So the numerator, what's the numerator? What are the coefficients of the numerator? Tell me the coefficients for the numerator.
That would be 1 and negative 0.5.
0.
0, yeah.
Okay. And the denominator? Denominator?
Plus 1, negative 0.4, and 0.5.
And save. Syntax error. Right there. Right. So see two zeros, one at 0 and one at 0.5. And then see two poles at 0.2. See that? 0.2, 0.2 plus J. Go up here. Yeah, see that? 0.2 plus J, 0.66. Well, if I go up a little, I'll get the 7. Okay. So yes. So you see the pole zero diagram shows the poles within the unit circle. Therefore, the system is stable, like I said. Any questions about this? All right. And I advise you to start that homework early. And then that test. Okay.
So for the homework, oh, never mind.
Excuse me.
Now, I was asking about the homework. So you'll mark everybody same question, or you'll be marking them simultaneously?
No, I'll be marking. I'm only marking one, and it'll be the same for everybody. So if you're feeling lucky, just do one. Yeah. I don't mean that, of course. I mean do
No,
both.
it's not say it's best to do it too.
Exactly. Exactly.
Use an eye on one you mark.
All right. So I'll see y'all later.
So no class on Monday, right?
Why?
I'll be your test.
It's a take-home test. Did you not read? Did you not read it?
No, I ain't read it yet.
It is due before 10 o'clock. Any other questions or concerns? Okay, have a good day.
You do talk, all right.